Good afternoon. I'd like to welcome everybody to the Health and Sciences Colloquium. Thanks for coming. I would like to present our speaker for today. This is Dr. Phil Troyk. He's the Associate Dean of the Armored College of Engineering at the Illinois Institute of Technology, and he's also a professor in the Department of Biomedical Engineering. He's also founder, president, and CEO of Cygenics Incorporated. It's a company that's dedicated to the design of custom integrated circuits for medical and industrial use. His research interests are very broad. He's got quite a long list. I'm just going to mention a couple of them. They include cortical and retinal visual prostheses, implantable EMG sensors, otherwise known as IMES, muscular activity sensors, and the design of neural prostheses. He obtained his Bachelor of Science in Electrical Engineering from the University of Illinois at Urbana, and his Master's in Science and PhD in Bioengineering from the University of Illinois at Chicago. So please join me and welcome Dr. Phil Troyk.
So I was asked to tell you a little bit about what I do in research, emphasizing those aspects of research that are distinctive from a more curriculum-based education. So I work in the field of what's called rehabilitation engineering or neural engineering. Actually, I don't even know where the word neural engineering came from. About 10 years ago, all of a sudden there was a word called neural engineering, and I found out I was a neural engineer. So I like to think a little more generically that there's a knowledge base, particularly in engineering and sciences, and that it's applied and the label that you use for it is really not important. So as was mentioned, I'm at the Illinois Institute of Technology in the Department of Biomedical Engineering. I've also been in electrical engineering there. And I do have a small company that designs and delivers integrated circuit chips for a variety of applications. And this is important because a lot of the research that I do has to transition itself to an actual deployed application. And to do that, you almost need a corporate structure. So what I'm going to tell you about today is a class of devices that are generically known as neuroprostheses. So I'm sure you're aware of prostheses, limb prostheses, different kinds of things. These are additions to the human body which are designed to either make up for loss or compensate for disease, and neuroprostheses are more different. These are implantable electronic devices that will interface with the neurological system, and these implants mimic neural behavior to compensate for deficit or disease. They may stimulate or sense. So by stimulating, they can introduce information into the body, and sensing, they can extract information out of the body. So they are kind of your real-life version of the Borg implants that you sometimes see on Star Trek. Now, some that you may be familiar with that you might not have thought in this category would include pacemakers, diaphragmatic pacers for pacing of the diaphragm, spinal cord stimulators for pain, bladder stimulators for incontinence, functional electrical stimulation devices for paralysis, cochlear implants. Some of you may know people that have cochlear implants for individuals who have loss of hearing. There's deep brain stimulators that can do almost miraculous things for compensation for Parkinson's disease, and vision prostheses, which I'll tell you something about. So this was the cover of Science magazine a few years ago in 2002, and they correctly talked about the bionic human, showing a range of devices that are either emerging or are available for use. So we really are getting closer and closer to thinking of cybernetics as a real-life, not science fiction paradigm which can be clinically deployed. So you see artificial hand, you can see here, this is probably an implantable defibrillator or a drug pump. You can see limb replacements. Here they're showing a mock-up of a vision prosthesis and a cochlear implant. This is a device here that I'll be telling you a little bit more about, which is an implantable myoelectric sensor. So there's a wide variety of these. And the list is quite extensive, and you can find many of them in typical web searches. And they can be subclassified as neuroprostheses can control bladder for people who either cannot control their bladder or are unable to urinate when desired, either problem. Hand and arm control, obstructive sleep apnea. Some of you may or may not be familiar with this condition. Sleep apnea is when you're sleeping and you stop breathing. And one of two things happens. You wake up or you die. And so a prosthesis has been looked at for sensing when your breathing stops and then stimulating the muscles of the throat and tongue in order to open the airway. Swallowing, there are people who have dysfunction of the recurrent laryngeal nerve and are unable to swallow properly. You can use electrical stimulation to compensate for that. Prosthetic control, I'll show you a little bit about that. Standing, stepping, balance, auditory pain control, even headache control. We designed an integrated circuit for a device that is now in clinical trials for control of migraine headaches. Neuromodulation means to modulate normal neural signals in the body using these type of implantable devices. So deep brain stimulation does that. With deep brain stimulation, you're trying to compensate for various diseases like Parkinson's disease or Huntington's disease, in which individuals have uncontrolled tremors in some cases. Epilepsy is another one where we're trying to sense seizures and then electrically intervene and terminate the seizures. Brain-machine interfaces, you may have seen or heard about some of those, where we're trying to capture the cortical signals of individuals and use that to actually control devices for people who are either paralyzed or worse yet, who are in what's called a locked-in condition where they're unable to communicate in a normal way. So the list is quite extensive, and it's really part of the research process that I was asked to talk to you about, which is why I like this field. There are different kinds of research. There's research in which you're focusing on fundamental, you're focusing on deployment. In the kind of research I do, it spans the process from invention to deployment. And by invention, I mean looking at a problem that exists, we then have to contemplate and invent a solution. From there, sometimes we have available technologies that we can simply take out of the toolkit and use in order to construct the solution we like. Other times, we have to do fundamental research to even explore if something's feasible. But eventually, something has to converge in a device that has an objective measure of function. It does something, it works, and it can be deployable in the clinic. So I particularly like this field because it goes all the way from the imagination point to the physical reality point. Now, it's always good if you can date your work, and if dating back to the Egyptians is always great. So I looked this up, and I found on the web here that there was an artificial big toe that was found in an Egyptian mummy that's on display in the Cairo Museum. And it's really quite a remarkable device if you imagine that it is a mechanical prosthetic device. What we are doing is taking devices that are not fundamentally dissimilar and adding electrical function to them. Now, perhaps one of the most famous attempts and devices that was ever implanted was that of a cortical vision prosthesis that I'm going to be telling you much more about today. And this was done in the United Kingdom in the late 60s by someone named Giles Brindley. This is a x-rays of the individual skull who had the device implanted. And what you see here is beneath their scalp, on their skull, are 80 packages the size of a quarter that were implanted. There were 80 electrodes, one package for each electrode. This was 1960s technology, but it was a remarkable achievement in that it was the first serious attempt to restore vision through an artificial device. Now, brain-machine interfaces have become very popular. They're the subject of medical research for individuals who have a paralysis, and this is again, off the web on the BrainGate system experiments that were done. But some of these others even span the idea of games. So the idea of having games in which you can control them cortically is quite popular. These are some slides from the Case Western Reserve website, and here they're describing limb replacement and functional electrical stimulation. For individuals who have lost limbs, and I'll tell you a little more about that in a moment, we are looking to replace them with robotic limbs. It's somewhat easier to do that than it is to figure out how to control these limbs naturally. For stimulation of paralyzed muscle, we're looking at trying to reanimate limbs that have lost their neural connection from the brain. This can happen through spinal cord injury or neural disease. Cochlear implants, these are from a variety of different websites here, and cochlear implants are some of the most successful neuroprostheses devices. They're about, I'm going to say about 25 to 30 years old. But it's a remarkable achievement. By stimulating remaining ganglion cells that are in the spiral organ with electrodes on a structure that is inserted, you can mimic the process of transduction of sounds to the generation of neural signals that eventually go along the 8th nerve to the brain. These systems are quite remarkable. There's about 35,000 individuals who are implanted worldwide, perhaps more, and many of them can talk on the telephone to people they haven't heard in 20 years and understand them. Unfortunately, they don't get much pleasure out of music because we don't quite understand how to make that neural interface for that type of information. Vision prostheses, there's quite a wide range of those, and these are from various websites from different groups that are working on them. Some of them work at the retina, as I'll explain. Some of them work at the cortex, as ours do. So when I said earlier that when we're faced with problems of this type, we look in our toolkit and we see what technologies do we have that are available that can be applied to solving some of the problems that are posed to us by these clinical conditions. And a very fundamental area of research is how to power these devices. Now, today, when we're thinking that all devices we walk around with have batteries and they're powered, and we don't think much about this, but you all well know that your mobile phones, frequently, the battery doesn't last for a day. And when you have an implanted device, you can't have a little door that you open up to swap in a new battery. So powering of devices becomes a very significant problem. For pacemakers, devices use an internal battery. That's called an active method. The advantage of that is that you have a power source that's available inside the body. You can get telemetry ranges, much like you could from Bluetooth or other kinds of technologies. But because the power source is implanted, it's limited to the length of time that power source will last. At best, 10 years for pacemakers. And you end up having larger size because you have to have the battery storage whose volume is related to how much capacity you will have. Another method is called passive. And this derives power from an extracorporeal transmitter, which means that there's a transmission device outside of the body that, in a sense, beams the power in wirelessly. The advantage is that you don't have the internal battery, so you can have unlimited lifetimes. The disadvantage is it's hard to get the energy in, so we often have short telemetry ranges that we have to deal with. But you can make things much smaller. Now, I want to tell you a little bit about this process because it is fundamental to the understanding of how these systems work. So typically, they are powered by a process that's called Transcutaneous Magnetic Coupling. And those of you that have taken physics may know the physics experiment of putting two coils next to each other, possibly moving a magnet through it like this, and seeing the response that you get from current induced in one coil that is then coupled to another coil. The same process happens for devices that are implanted in the body. We have an outside device that creates a large magnetic field by having a large current pass through it. This magnetic field easily penetrates the tissue, can be coupled to a smaller coil that's inside of the device, and in this way we can transfer energy to the device. Now what's convenient about this is then we can change the transfer of the energy in order to communicate with the device. So we can put a carrier, if you will, on top of the wave that is carrying the energy. We can use the same link to communicate from the device back outside the body. So with two simple coils, we can have a very effective power and communication range. Now, why do we have to do this? Why can't we just use implanted batteries like pacemakers do? The problem is that the capacity of present battery technology doesn't meet the needs of neuroprostheses of any kind. And the reason for this can be seen just by looking at numbers. Pacemakers typically will pace about 1 pulse a second, maybe a couple of channels. Neural prostheses, in order to communicate with the nervous system, may have hundreds of pulses per second and many, many channels or many, many output data channels, and the power that would be in a pacemaker battery would simply be exhausted too quickly. So some people have proposed and even implanted percutaneous connectors. What this means is percutaneous means through the skin, so it's a plug that's on your head or somewhere else, and you plug into the device, and that's how you make the communication through the skin. This is very problematical because the body doesn't like holes that are in its normal barrier, which is the dermis. And so therefore, it's not regarded as an optimal solution. There's experimentation going on for optical powering and microwave powering and capacitive coupling powering and a lot of other things that right now are not presently practical. So the features of this is that it's fairly easy to do this. You can couple significant power across the skin. It's conceptually simple. It's a transformer. That's what it is. And it's been in use for devices for over 50 years. So the problem that we face is that as the distance between an outside coil gets bigger and the implanted device gets smaller, it gets harder to transmit the energy. So let me show you how this actually can work. Okay, so this is a device here. This is just a crude magnetic field generation device that I'm holding. And this is a coil of wire, and I have it attached to a light bulb. Okay, and when I push this button and bring it up, I can transfer the energy to this little lamp, and I have it pulsing on purpose so you can see it. And you can see here that as I get away and as I come closer, I'm able to induce more energy into that coil. Now, this is a rather large coil. You can do it with smaller coils. Here's a smaller one. And I think you can see the little pulsing going on. And for those of you that may have good vision, you can do it with very small coils. And it works with this also. Can you see it blinking in the back? It's remarkable how good your eyes are, isn't it? Yeah, especially when you're 20 years old. So this shows you right here the fundamental feasibility of what we need to do. This is a very tiny device. This is a device, in fact, I'm going to tell you about. And we're able to communicate enough energy to this device to make it sit there. And the blinking is representative of the commands that we would send into the device. So armed with the knowledge of this, let's see what can be done with this. Now, this is addressing the problem of an amputee. Here you see an individual who suffered from a bilateral upper limb amputation due to an electrical accident. This is a common type of amputation, particularly for electrical workers. The two appendages are unfortunately a fairly good conductor, and they suffer dramatically, and the limbs can be so damaged that they have to be amputated. So if you go to a rehabilitation center and you have a limb amputation, this is what you get. You get a hook and a wire. This is 1950s or earlier technology, but it's extremely reliable. And the majority of people who get amputations have devices of this type. And you see you can hook extra kinds of tools onto it. But it's very convenient. Farm accidents from farm implements are another cause of amputation. And for the farm worker or the farmer who's in the field who suffers a problem with their prosthetic device, they've actually been known to take a piece of baling wire and fix the cable. So this works by transferring movements of other muscles that are in the chest along a cable to the hook to open and close. That's kind of the state-of-the-art technology. Now, what is being worked on and what is even being clinically deployed in some places are robotic limbs that can move, much like you've seen in science fiction, such as in the Luke Skywalker, I am your father, this is your new hand, okay? So these are not entirely science fiction. And these are slides from the Rehabilitation Institute of Chicago. Here, these are artificial robotic limbs. This is an interesting slide. Does anybody in this room know where that slide is from? Huh? Do you know? It's a television show. You probably predates any, huh?
The Bionic Man?
Yes, it is. There you go.
I just guessed.
That's the one there, which is we can rebuild him, we can make him better than he was, and that's the picture they show, and there's the limbs. So you can see that science fiction is often the inspiration for many of the things we do. Now, the state of art of artificial limbs is such that they're actually pretty good. There's a range of very elaborate limbs that have movable fingers, that can have 18 motors in them, that have the prospect of offering a near lifelike replacement. And it's much easier to design the mechanics of the limb than it is to figure out a way to control the limb. Because it's not of much use if you can't control it in a way that you're used to doing using signals from your brain. Here are some other examples. These are very elaborate, very high-priced, state-of-the-art limbs that are being researched that have 18 degrees of freedom. That means they have 18 separate movements that can be done in a artificial hand and wrist. This is from a project that was funded by DARPA. This is a robotic arm showing on a dummy to replace the hook and wire. Interesting thing about the project from DARPA, one of their measures was, is the individual with the limb able to assemble and disassemble a weapon? That was one of their tests. Now, in determining how to control these, we go to the source. What are the signals that naturally controlled the limb before there was amputation? So these are called myoelectric signals, or EMG signals, electromyographic signals. And these are the electrical potentials that muscles produce as they receive the impulses from nerves to cause them to contract. And in the residual limb, there are residual muscles. And those muscles are still connected to the nerves, what's left of them, that go to the brain, and you potentially have the signals going to these amputated muscles that used to control the hand. So I'm sure you know from some of your classes that the muscles that make me do this are not in my hand, they're in my arm. And the tendons connect down here, and they pull on that because I couldn't possibly have enough muscular strength in my arm to do the gripping forces that are required for us biologically. So these muscles are all down here in the arm. And even if I get an amputation, if some of those muscles are left, maybe I can extract signals from them. So the idea is that if we try to extract those signals, we could use them to control the prostheses motors. What is typically done is to try to extract muscle signals from the surface of the skin of the residual limb. Okay? This is done in a way to say, okay, the muscles are there. If I put electrodes on the surface of my skin, a normal person, and I move my arm, you will see electromyographic signals. Can I sense those with electrodes on the surface of the skin? And yes, you can. The problem is you can only get a very limited number of sites that are separate and separately controllable, because you have these muscle groups in there all sort of mixed together, some of them in a certainly compromised state, and when you try to extract individual signals, it becomes extremely difficult to do that. Now, in the forearm, you have up to 18 muscle groups that are available that used to control the hand. So if we could get sensing devices inside of these individual muscles and then wirelessly communicate the signals that they're sensing to a device on the outside of the limb, maybe we could get much more enhanced function. Now, to digress a little bit, we often look to technologies that are available when trying to do a new device development. So some of you may be familiar with what's called RFID. If you have a PET, and if you have what's called a chip in the PET, this is RFID. It's called radio frequency identification. What these devices are, they're small, tiny capsules which can be injected through an injector into the animal, and with a reader device, you can power it magnetically, just like I showed you, and you can communicate with it. So that sort of sounds like, well, if I have a device that can be implanted, that I can power, I can get a signal back from, that in this case is a serial number, maybe I could have the device sense muscle signals and send muscle signals back instead of just a serial number. Here's another picture of a device, just to show you the size. What these are little glass tubes that have electronics inside. Here's the little coil that we were talking about that I was showing you for the coupling. It turns out such devices exist. We developed them at IIT for both stimulation and sensing. This is the one that was in Science magazine for stimulation. The idea here is that these little capsular devices could be placed into either paralyzed muscle or residual muscle groups from amputation, and we could either stimulate paralyzed muscle or record from intact muscles by wirelessly powering and communicating with them. If we could do that, we could possibly achieve the idea of going from this to something where we have an artificial limb. This is the state of the art now with surface electrodes. What we want to do is turn this into something that would have multiple sites. So now we go to sort of a conceptual phase. This is the invention part. I need something that can get signals from the brain to control my hand. What could I get? I need a little gadget I could put in the body that I could power and talk to. That's sort of all kind of fantasy, right? Now we have to move it towards how could it work. So interestingly, I showed you the experiment with the coil. The artificial limb is uniquely configured because it has to encircle the residual limb. It has to stay on the body that way. It gives us the opportunity to put a coil inside of that and then put these little implants inside of here, which are just about the same size as the little thing I showed you in my hand, and then we can power them, talk to them, get signals back from them, and use them to control the artificial limb. And that's the basic concept of what's called the implantable myoelectric sensor. We can use each one of these as a command source now to control a complicated limb. Here are such devices for real. This is what one looks like inside. It's a ceramic tube. It has electrodes at both ends. Inside, most of the volume is occupied by a coil, but in the middle of this coil is an integrated circuit that we designed in order to be able to process the signals from the muscles as well as coordinate the transfer of energy from the outside. Here you can see them being held. Here you can see them next to a penny. Okay. Now, to test these, this is from the University of Utah, some of these were implanted in the forearm of a rhesus monkey. And the animal was trained in a task in which they had to move a manipulandum in order to perform a certain task. The signals were then recorded from the normal arm, and then they were played back to a robotic arm, so that the animal now, even though the animal thought they were moving their limb to actually do the task, it was really controlling the artificial limb. Here you can see them in X-ray, implanted in the monkey's arm. Here's another X-ray showing them. And here, this is an interesting movie. It shows that as the muscles are contracting, you see the devices. And I'm going to play this again, or it plays again. Watch very carefully here. You'll see one of them slide. They're right there. Just see it? The device slides. It's moving with the muscle, which is very, very convenient because it's an untethered device. There's no cable to hook up. There's nothing to pull or disrupt. These little things just float with the muscles and pick up their signals wirelessly. Now, what can we do with them? Okay, well, here are these things that we call EMG signals. And these are recorded in the muscle group for each of the digits of the monkey. Here's the index finger, the middle ring finger, the middle flexing finger, and the ring pinky extensor, and index finger and extension. This is index finger flexion, index finger extension. So extension, flexion, extension, flexion. So these are the actual signals that were recorded by IME's devices. And now we process them. And these are the processing of them. And we say, okay, when are we activating a finger and when are we not? So in this case here, you see we're extracting from here and we're saying all fingers are being sensed, that we have activity on all fingers. Here, we're seeing that we're sensing only the index finger inflection alone. So this is showing us the capability of these devices to be highly selective in extracting these signals from the muscles. Now, now that we've talked about them functionally, here's what they are physically. They're these little things that are stuck inside of these tubes and sealed up. Here you can see a much more blown up picture of it. And this is very fine wire that winds this coil. This wire is 25 microns. And as a frame of reference, one of your hair has probably a 100 micron diameter. So it's very fine wire. We have special machines that wind them. This is an integrated circuit chip that we designed specifically to perform the functions that are needed. And this little section here is its own little computer brain for it. We design integrated circuit chips by going through a electronic circuit design and simulation process, and then we lay them out in a graphic format. We email off the file, and our chips come back in the mail. It's as simple as that. Now, these are planned to be used to control some rather sophisticated arms, and these are arms that have been developed by a DoD for replacement of limbs in returning warfighters. It's unfortunate, but Kevlar bodysuits and helmets have been very successful in preventing the death of individuals who are in battle. What's left are the limbs. And so now there's an uncomfortable number of individuals who have come back from conflicts that have amputated limbs. That being said, this is a sobering comparison. This is an individual called John Culahan. There are two covers of magazine articles that were written about him. He was one of the trial individuals working with one of the advanced arms designed by DARPA. There was a lot of press about him. He was on TV. This is what he uses in real life, a hook and a wire. So we still have some ways to go. Okay, I'd like to shift gears a little bit and tell you about another type of prosthesis topic called for vision prostheses. So for those of us who work in neuroprostheses, restoration of vision function is the holy grail of neuroprostheses. This is the concept. The idea, and this is our concept, the idea is that a camera captures the image, it communicates it to wireless modules that are powered and communicated with just like the IME's devices, but now each one of these modules contains 16 sub-miniature electrodes, and if you could look at an electrode next to the size of a human hair, it would look like this. Those electrode modules, complete with a coil and electronics, are inserted into the cortex. They stimulate neural signals, and the idea is that if we can understand how to talk to the brain, we can create the perception of the image in the person's brain. Now let me digress slightly and talk about vision a little bit, because it's not something that we think about in a functional way. We take it quite for granted. Half of the primate brain, your brain, is dedicated to processing vision in one form or another. That's a lot of neural machinery that's going to process vision. Now, how does vision work? Well, you don't have a little screen in your head, and you don't have some kind of homunculus guy in your head looking at what's on the screen. Vision is a perception. And so how that works is that light enters the eye, it hits the retina, it creates a volley of neural impulses which are then communicated to the brain. The brain then takes those signals and uses them to extract features. features about where the stimulus is in the visual field, about is something moving, what angle is it at, what color is it. It takes all those features and then passes those on to higher centers of the brain, where it then assembles the perception that we think of as vision. So what that means is that your perception, my perception cannot be the same. So when I tell you that's yellow, how do you know? Because somebody told you it was yellow. That's why. Your perception of yellow and your perception of yellow are different. Maybe that's why certain individuals that we call artists are able to do things with manipulating vision perception in ways that the rest of us can't. But nonetheless, vision is a perception, and as you look at me right now, your brain is making most of it up. Because your brain isn't fast enough to process it on a bit pixel by pixel basis coming from the retina. Too much information. Your brain is taking what's in, it's matching it to templates that you have in memory, and it's making up and enhancing the perception that we call vision. And some species are tuned in order to have their vision system behave in a certain way. You may have heard the story of a frog. If you put a frog down and put dead flies in front of the frog starves. Because the frog's vision system is tuned for small objects that move. That's what it's tuned for. It's not tuned to look at small objects that are static. Now, if we think about blindness, it's something that many of us, don't even think about really in a comprehensive way. But the impact on society is pretty great. If you use the every so many minutes analogy, every 7 minutes, someone in this country becomes legally blind or severely visually impaired. Now, there's different levels of blindness. Legally blind, visually impaired, totally blind. But nonetheless, currently there's 10 million Americans that are affected by some form of severe visual impairment, and 1.6 million are totally blind, which means they have no visual perception at all. The numbers are growing, and they're growing because population is aging, people are living longer, and there are age-related diseases such as retinitis pigmentosa, macular degeneration, that are all now causing blindness to increase in its prevalence in society. But there's still a number of school-age children who have blindness, typically due to birth situations. 70% of working people with blindness are unemployed. Most of those will be unemployed for their entire lives. The annual cost to the economy, and this is a few years old, is greater than $4 billion a year, but that's only money. On a personal note, there's social isolation. It causes depression, a disconnection from others. I would challenge any of you, close your eyes and keep them closed for the whole rest of this talk. You'd probably have a hard time doing it. There's a natural urge. Your brain wants visual information. That's the way it's wired. Worldwide, it's even more pronounced here. We're just a tiny little slice of vision loss in the world. In other areas of the world, it's much more dramatic. And a rather staggering fact is that in developing countries, the expected lifetime of a child with blindness is less than 1 year. And it is thought that that has to do with the inability to cope socially with the implications of the blindness. So, what could we do to try to restore vision function? It's an admirable goal. Okay? Well, the idea is that what's wrong is that the connection from the eye to here is interrupted. It's interrupted at the retina. It's interrupted at the optic nerve. It may even be interrupted due to damage of the cortex. So our idea is to go in with artificial information, bypass the area where there's damage, and communicate the artificial information directly to the vision system. Now, these devices have to be 5 to 10 times more dense physically and electrically than anything we built before, which is a major challenge for those of us in the field. Now, this is from Netter, the famous artist, and this is the vision system. And we could try to put information in at the retina. And there are approaches to do that. This is from the second sight group. This was from Optobionics, which is no longer in existence. But the idea is that if we put electrodes on the retina itself, when we stimulate, we can reach residual neural cells that are there and cause them to be activated. If we can do that in a meaningful pattern, we can therefore introduce vision information. The idea is that you would have something that topographically would introduce the information in a spatially correct manner to the retina using artificial optics in order to bridge the connection. The next place we could go is to the optic nerve. And there are groups that have and are trying to do that. You could, in fact, go to the optic nerve. This is a slide from the Belgium group that did this in 2 individuals. And you can put electrodes around the optic nerve and try to communicate vision information to the optic nerve that way. You can also go directly to the brain, to the cortex, and that's the approach that we are working on at IIT. I showed you this before. This is the picture from Giles Brindley. 80 electrodes that were implanted in the brain. You can see the little dots of the electrodes. Here's a cable that connects it. Here are the packages beneath the scalp that this individual had. 1 package for each electrode. That was the only way in 1960s they knew how to get channels to the electrodes. Now we can have 1 link, 1 device, much smaller than that, and we can get multiple channels. So are these devices technically feasible? Well, we are using an approach that's called the intracortical approach, which means that electrodes are actually inserted down into the cortex. The cortex has layers, and we are looking to get to what's layer 4, which is where the signals come in from the optic nerve. So what happens is that from your optic nerve, it's relayed through an area called the lateral geniculate nucleus in the brain, and then it's projected to the cortex, in which from there the features are decomposed and it's communicated to the rest of the brain. So this, what's called area V1, is the primary relay station for all the information coming to your brain. The idea is that we stick modules in here, we communicate directly with the brain. Now, in starting to do this, this has been a long development that has spanned several decades. And electrodes were first put together in little groups like this and hand inserted into the cortex. Then it was recognized that we'd have to have a much more efficient way of inserting these electrodes in groups. So little electrode arrays were developed in which the electrodes were sculpted at the tip to be of a specific shape to minimize damage. Here is a monkey brain that we did some work on, and here you see electrode arrays that are there, and each one of them have 16 electrodes. But what I want you to notice are all the wires. Those cables are actually pretty small. They're less than 1 millimeter. But this is only for 96 electrodes. And conservative estimates are that we might need 1,000 electrodes before we could get any usable vision function. You'd have this massive cables that would all have to go through the protective layer of the brain called the dura and enter into there. It would be a mess. Here's a real human brain, all kinds of blood vessels on the surface. It's a real surgical challenge. So can we actually have modules that are connected by little cables to some sort of a little package that has a battery in it? It's just not feasible. So we had to invent a new technology. And what we thought of was wireless 16-channel little modules. Each one has its own address. Each one can talk to one of 16 electrodes, like a little cell phone network in your head. It'll use the transcutaneous coupling in the same way that I showed you earlier. And such devices now exist. This is a schematic of it. We have the electronic chip. We have a little platform. We have electrodes that are there. We have a coil. We have a chip, electronic chip that goes on the back, and the whole thing is packaged up as a little module. Here you see some other pictures, and I'm going to tell you about these electrodes in a moment. Here's the integrated circuit chip. This integrated circuit chip, this is a picture, a drawing of it. All the blue stuff is wires. This is all digital stuff. Here are the little cells, 16 of them all around, that talk to each one of the 16 electrodes. This is what it looks physically from the side. You can see there's a platform, electrodes, there's a chip, there's a coil. That's packaged in a way to protect it from the body fluids, and that gets inserted. Here's a real one. Here's what they really look like. Here you can see the chip, here you can see the bonding. Here's a finished one. That's a dime. Here's a little coil around it. Here's the electric chip. Let me just say that the process of sticking in signals through electrodes is not something that's straightforward. And in general, electrons flow in wires, but they don't jump out of the wires and flow into your brain. Ions flow in the brain. That's what carries current in fluids is ions. So electrons in wires, ions in tissue, the electrode has to convert electrons into ions. And it does this through electrochemical reactions. Some of you may have had chemistry, you may have had electrochemistry. You look at the valences, you count up the charges on both sides. Well, they do the same thing. And the trouble is that doing this process produces the potential to put unwanted constituents of the reactions into the tissue. Let me kind of jump to, yes. And so let me show you the result of what those unwanted reactions could be. If we force current to flow when the electrochemistry can't support the current to flow, some rather interesting things can happen that are not very desirable. Here is an electrode in which we are purposefully exceeding the electrochemical limit for that electrode, and it's producing gas bubbles. And that's a very easy thing to do, and it's very easy to exceed the limits without realizing it. So if you had one of these in the brain and you started stimulating next to those poor little neurons that are there, and you started producing these gas bubbles, it would be like putting sticks of dynamite in there and blowing them up. So this is a major problem. And in order to solve this problem, a material was developed called activated iridium oxide film. Here again, we're stepping back to a fundamental research to solve a problem that we're faced with in the course of a development. So this was digression. Now, some very smart people who I knew, Lois Robley is still alive, developed this material at a place called EIC Laboratories. And what it does is it puts a coating on the electrode, and it allows the electrochemistry to happen in this coating rather than in the tissue. And it acts as a little buffer zone, and it protects the tissue. And in fact, it works very well. Now, it's using a metal called iridium. Here is AIROF microelectrode. This is 20 microns. Remember, your hair is 100 microns, 5 times as big as that. Here's the electrode sculpted. Here's the iridium tip. This is insulation. The current comes squirting out here. And this black stuff, that's the iridium oxide film. Turns out it's electrochromic. You can make it go light to dark, depending upon how you control it. Now, things can go wrong. This is a normal AIROF electrode. This is an electrode that's been abused. So you have to be very careful when you stimulate these in the brain that you don't overstimulate, or you can destroy the electrode in an irreversible way. Here again is the size of the electrode compared to a human hair. Now, iridium is kind of an interesting topic because how many of you know where iridium comes from? Yes, but how did it get there? Yeah, those of you who watch Discovery Channel know that the prevailing theory is that when the asteroid hit that wiped out the dinosaurs, it threw a bunch of iridium into the air that came from the asteroid, and it settled in the KT boundary. So iridium is in the KT boundary of the Earth. So we like to say that to develop our neuroprostheses, we're using material that came from outer space. But unfortunately, 90% of the life on the planet Earth had to be wiped away in order for us to get it. Now, the big question is, if we make gadgets we can stick in the brain, can we estimate their functionality? Do we think they'll work? Okay? So we'd like to think that if we started with an image like this, that with a vision prosthesis we could do that. For what we know now, we'd be lucky to do this. And let me tell you a little more about that. This is from some work a colleague of mine at Johns Hopkins University, Jalan Danieli, and here he's done work with normal individuals in which he presents to their eyes the simulation of what we think artificial vision would be like. So imagine if you had a soda straw, and at the end of the soda straw was a little screen So the world looked like a bunch of little dots, and you moved the soda straw around like this, and then the image was built up in your memory. That's our best understanding of what artificial vision is like. So he does these tests with normal people in which he will show them 4 faces and then show them one of those faces using the artificial vision means. And the person has to then identify which face that was. And then what can be done is we can change the pattern in terms of the size of the simulated vision percepts, the dropout, the ones that are dropped away, the spacing that's there. And the question is, how well do people do in identifying the faces, which is a very important function for us, to identify faces. These days, we don't need a vision prosthesis to read. We have other technology for that. But face recognition is very important to us. So you can play this game, and you can keep going, and I'll just show you a couple more here. So you can see at what point does it become impossible in order to identify the face? At what point is the vision information so sparse that we can no longer provide sufficient information to the brain? And on this last one here, you can see there are only 2 gray levels, on or off. And you can see it becomes increasingly difficult. So we can play this game of trying to simulate the vision to understand how we might communicate to the brain and how much information might be needed. Now, when we stimulate the brain, you get little spots, one for each electrode, and they're called phosphenes. And the idea is that with a collection of these little spots moving around in the world, you could then make up the image in your brain. When you do it on the retina, you get that little grid pattern that I showed you. When you do it right at the brain, you get a very distorted pattern. And here is such a distorted pattern of what you would get from an image if you stimulated on the brain with a regular grid. And that image came from this person, and it would look like this. And it's what's called a typical hourglass image, which is caused by the distortion of the mapping from the retina to the vision cortex caused by the branching of the optic nerve. Now, we looked at where could we put electrodes on the vision cortex. Surgically, where could we put them that would be safe and would justify an individual volunteering? We decided that the dorsolateral surface of the occipital pole, you have 2 occipital poles right back here. The dorsolateral surface, kind of the surface up on the top here, is where we could put electrodes. There are various surgical reasons why you don't want to put them in other places, because there's blood vessels going there and everything else, and we've exhaustively talked with our surgeons about that. And so the question was, if we did put them on that occipital pole, and we did these kinds of simulated tests, what kind of vision might you get? So we did that, and we did a rather elaborate experiment in which an individual has a pair of virtual reality goggles. And those virtual reality goggles present to their eyes a simulation of the artificial vision. And then we ask them to do things, and we see how well they can do them. It's a complicated task, which would take too long to explain here, but let me just show it to you. So here the individual has the headgear, and they have in front of them a checkerboard. And their task is to put black checkers on the white squares. That's what we've asked them to do. And this is what they see. And so if you look as the person's moving their head and scanning around, you can see every now and then they will go by the corner of a square, and they'll kind of guess that there's a square there. And you can see here the person is now managing to find that one, and this is called the placing task. So we can obviously randomly change the checkerboard, so they can't memorize the checkerboard, and we can see how long does it take for them to do that. You, with your normal vision, you'd be able to very quickly put those checkers there. How long could a person with artificial vision take to do it? So this is a way that we can use to objectively measure the possible utility you could get from such a device. Now, these are curves that I could spend a lot of time explaining about, but they tell you one thing, and they tell you one thing that's very important. That is, up here we have the time that it takes for them to do the task of moving the checker onto the square. And on this axis, we have the number of visits that they made. In other words, the number of times that they tried it. And what you see, no matter what kind of variations we do, the longer they can use it, the better they become. And the whole idea of a vision prosthesis has to rely upon the ability of the brain to adapt and learn. If we don't have that, the performance will be too sparse. However, the vision system, the brain, wants information. It's begging, it's screaming for information. And if you give it information in a way that it can use it, and that's the key to figure out how can we communicate so it can use it, then we can actually get to some function. These individuals were able, after a period of time, to be able to do these in less than 11 seconds. They could move the checkers to each square, no matter where we put the square, a new checkerboard each time in less than 11 seconds. Well, then we gave them another task, and we gave them a virtual maze. And this was a computer-generated maze where, with a joystick, they had to navigate through a maze, and they had to find a letter on the wall, identify that room, and then go through the maze and find the next letter. So you see here, they're looking for B, and we put up little vision obstacles for them just to make it harder. Okay? And of course, we can change the maze all the time, so they can't memorize it. This is what they see. And after they've worked with this a while, they're able to go through 20 seconds per room. They're able to find the next room. So this gives us a lot of anticipation and hope, if you will, that with this sparsity of information, that we could reasonably communicate. With the technology that we think we can have, we could restore vision function. One last thing I'll mention to you is stimulation of the spine for restoration of walking. This is a project we have with the University of Alberta. Individual in a wheelchair, not able to walk. This has been another dream of people, if you will, make the lame walk, the blind see, and the deaf hear, to use a biblical reference. Okay? So restoration of walking is something that is also very much on the minds of people doing research. The idea here is to use tiny wires that would go into the spinal cord to activate circuits that are present in the spinal cord but have become disconnected from the brain because the spinal cord has been injured. Spinal cord injury. A large fraction of them are gunshots. A large fraction are sports accidents. Hang gliding, by the way, really high percentage of people who hang glide get spinal cord injury, so think twice before you do it. The idea is that you could put fine wires in here, have one of these devices that we power and communicate with, and restore the walking. Here you see some actual fine wires in a cat spinal cord. Very fine, very difficult to put in. And these are experiments that are done where we instrument the leg of the animal and see what type of walking can be achieved. And they're doing pretty well. We developed the devices. Here's a device being developed for the animal experiments. The fine wire is coming off. This is a little cap that goes on the spinal cord, a coil that sits up there that we can use to talk to it. Here's the chip we designed, 16-channel neural chip that we designed to be able to operate it. I think you're getting an idea of the kind of research I do. I look for problems that exist. I look for applications that don't have solutions. I look in my toolbox to see, do I have a tool I can use to solve it? If I don't, we invent the tool, we develop the tool, and in the end, we hopefully make the difference. Now, for us, using the technology platform is what's important. How many things can we apply our technology to? Here are these electrode arrays that we make. Tiny little things, tiny little electrodes could go in. You'd think it's got to be good for a variety of things, and we're looking for those things. We can put electronics on the back of them. That's in our toolkit. We're looking to the day where you will have wireless modules implanted in the brain with little discs on the outside that will communicate with them and produce the kind of cybernetic interfaces that right now are part of science fiction. So in thinking about this, you might think yourself, what kind of neural deficit problems might you imagine being addressed by neuroprostheses? Which ones do you think a person with paralysis, for example, would find the most important? You might say, well, they want to walk. That isn't necessarily the top one. Sexual function is pretty high up there. Okay, for people who have spinal, can you give me sexual function? I don't care if I can walk, okay? Give me sexual function, okay? You might think that controlling your bladder is very important, but we had a rather illuminating presentation from someone once at a major conference where we were talking about bladder prostheses, and she said, right now, I use a catheter in a bag. Right now, I control when I need to go empty that in the toilet. You give me a bladder prosthesis, you better fix my arms. Because if you don't fix my arms, I can't transfer myself to use the toilet. So you haven't done anything for me. So the application of these things is often not quite as straightforward as you might think. What methods do you think would be needed to implant electrodes into the brain? We're inventing new surgical tools, new surgical methods, because you don't just go in there and stick these little needles in the brain, you get bleeding all over the place. What physical restrictions would have to be placed on them? What size would they be? Do they have to be wireless? And how would they have to be configured for the patient or the user interface? Rehab hospitals are filled with cabinets full of junk that nobody wants because it wasn't suited for their use. This is a very important part of research. It involves psychology, it involves user interfaces, it involves the type of cross-disciplinary study that is very popular today in learning. I think that's my time, and I'm happy to answer questions and to give a demonstration of surface electrical stimulation if anybody would like to see it.